Thank you very much. Thank you for organizing this nice event. And since I'm the last speaker, the next session is organized by the organizers themselves. So maybe we should all thank all the organizers for this nice week. So this is joint work with Frank Ball. We haven't submitted it yet, but we have tried to submit it to ArcSci, but we've been denied. So I've entered a new level of humiliation. That's when you're not even accepted to ArcSci. I don't know why. I think it has to do with I wanted a different subject classification than their algorithm wanted. But anyway, I can send you the paper if you're interested. Before I start, I want to say a few words about, or just a couple of words about ESPIDAM. We organized this workshop, the first European program, summer program for infectious disease modeling, highly inspired by the SISMID in the US. So it took place in Stockholm in late June. I think it was a great success. We had 6 courses. They're quite long courses, 15 hours, so you really get to learn some stuff. Great instructors, 4 are here beside myself. It's Simon Corgemet and Lorenzo Pellis and Sebastian Funk, who has left, and also some other listed there, but there were 12 instructors, so I don't list all. And we received quite a lot of attention, 95 participants from 18 countries. The plan is to do this also next year, so if you're interested, stay updated with that. Okay, so this presentation is about social contact studies and how to make use of them. In several of the presentations we have heard about contact matrices. So that relates to social contact studies. Before that, I'll just show 1 or 2 slides about multi-type epidemics models, because that is what is used when you use social contact matrices. So a multi-type epidemic, that's when you classify individuals into different types, and you assume that the contact rate between an I individual and a J individual might differ between the different types. So the homogeneous model says everyone has contact with everyone else at the same rate, but in a multi-type setting, it might be that if kids might have more contact with other kids as opposed to with 50 to 60-year-old people or something like that. And this, in many books, it is called has an infectious contact. So you might think of this beta star being an actual contact rate multiplied by the probability of an infection given such a contact. Later I will assume that this does not depend on the different types of individuals, but in principle it can do. So what about these models? Well, if you know this contact rate, I forgot to say that you need to know something else. You also need to know how many individuals or what fraction of the community that belongs to each type. Without that information, you can't make any progress at all, but usually you know from the statistic bureaus how many people have, what fraction of the community are between 0 and 10 years, and what fraction is between 11 and 20. So if you know this information, you have this contact matrix, and then you also need to know what is the transmission probability, which that was contained here, but this 1 over gamma is the duration, the average duration of the infectious period. So if you know the transmission probability, and you know the rate at which individuals have contact with each other, you know the population fractions, and you know the average duration of the infectious period, then you know what is the reproduction number. That's the largest eigenvalue to this next generation matrix. You can also, if you do a probabilistic model, you can say what's the probability that the epidemic takes off. And you can also compute what fraction will get infected, and that's the solution to this set of not differential equations, this set of equations. Okay, so if you know the contact matrix, you know what fractions in the different categories, and you know how long you're infected, you can compute the basic reproduction number and how many that will get infected. And you can extend this to more SCIR models, and you don't need to have the Markov assumption. It still applies. As I said, I will skip here. So in principle, you could let this transmission probability be some overall average transmission probability multiplied by the infectivity of the type I individuals, the average infectivity multiplied by the average susceptibility of J individuals. But for now, I will set these equal to 1, so we just have one transmission probability. And an important feature is that the contacts, that's symmetric. If I contact you, I have contact with you, you have contact with me, the transmission probability might be unsymmetric, but I will assume this to be symmetric as well. Okay. So that was an interlude, but in order to say how these social contact studies have been used in epidemic modeling. So I think it started 15 years ago with the polymod study, and there has been many similar studies, in particular during the pandemic there were. So what are they? Well, usually you interview some people, or not, well, first you interview them, but then you let them fill out their contacts during typically one day. And not only who they have contact with, but also what ages they were, and maybe if they belong to the family or not, and some other, how close was the contact. But I will skip those details. I will just keep track of the age and how many they had contact with of different ages, and that's what most others focus on as well. And this close contact is a well-defined thing. Usually it's a face-to-face contact within 1 meter for at least 2 minutes, or some similar definition. There's a very nice page, I think is maintained by Neil Hens, where you find a lot of these contact studies, by the way. And that's where we have also made use of some of these contact studies. So here is how such a data file looks. So this is the individual one. There's a separate file which has information about the different individuals. But here you have individual one. The first contact of individual one was with someone who was 4 years old. You might guess that it was the child of the person or so, and it was a male, and I don't know what the other things are. The second contact was someone who was 6 years old. That was a female, and then one 36, 32, 30, 65, 62. And those were the 7 contacts that the first individual had. And then the second individual, and it goes on for a long while. So that's how this data looks like. Statistics is about summarizing data. So the most common way to summarize this long list of data is as follows. Usually it's a matrix, here it's a heat map, but this is from some other journal. So it's a heat map, and what does it show? It shows that the majority of the contacts are with people of your own age. And that here you have the parent-children type of contacts. I think these might be the grandparent thing, but I'm not sure. Also, if you look at the total number of contacts as a function of age, it has this typical structure that it goes up, but then it slightly goes down. I'm somewhere here, so I'm heading downwards, unfortunately. But so the overall number of contacts is more. They have higher number of contacts among the younger age groups, and then it goes down. But also with whom you mix, this is called assortativity with respect to age. So you tend to mix more with people of your own age. Okay, so this was has been used for quite a long time now, 15 years or so. And so the data you get from this is, or the way to summarize it is that you compute the average number of contacts that I individuals have with J individuals. And in terms of the other notation, you have to multiply this individual contact with a fraction of it. So with this contact matrix, and for some hypothetical disease model which has transmission probability P and mean duration 1 over gamma, you can compute what is R naught, what's the probability of an outbreak, and how many that will get infected. And this has been used, and it has improved the modeling of infectious diseases, I think, in general. And what is the difference? Before, people just assumed the average number of contacts, but now we acknowledge the age and this sortativity, and that there is variation in number of contacts. So what are the typical conclusions? Well, the conclusion is that if you admit this age discrepancy, typically you get a bigger value of R naught. How about the final size? Well, that's not, it depends. If the transmission probability is small, then you get a larger outbreak if you acknowledge the age groups. Whereas if the transmission probability is large, you actually get a smaller outbreak if you acknowledge the age groups. So this seems like we have done nothing. This is a summary, but what we have considered is the following then. You lose quite a lot of information, as you do with all statistics, because statistics is about summarizing lots of data. But what do you lose when you merge this large data set into the average contact matrix? Well, what you lose is the variation within age groups. That's not contained in C. So the question that we addressed here is, can we use more information from these social contact studies to improve the analysis even more? And does it make a big difference or not? And the answer is yes to both of them, that we can do more, and it actually makes a very big difference in the empirical data sets we looked at. So here is one set of data. It comes from a French study, I think. So here is one way of plotting the data. Each cross here is one individual. Here is the age, and on the y-axis it's the number of contacts. So in this figure we don't see, so this individual was 60 years old, it had 100 contacts. We don't see who they were they with young kids, but that's contained in the data, but it's not shown in this plot. So we see this, the average number here is slightly bigger and it starts dropping here. I think this is superficial, but it seems to go up. I don't think that's a typical thing. So it goes down. So that agrees with what I said. But what you more see here is there's a huge variation also within age group, which is lost if you only look at the mean matrix. And here is the mean matrix offspring. It's slightly blurred, this diagonal, because the age groups are, you see this huge age group, so that blurs this diagonal thing. The reason we chose these age groups is that was chosen in the original study. So, what did we do? Well, we analyzed this data in 4 different ways. First, neglecting any heterogeneity, so just looking at the average number of contacts and see for a given P and a given infectious period, what is R naught and how many will get infected. And then we analyze it admitting the age heterogeneity, so what has been done before. But let me start here. So the homogeneous model, the overall average number of contacts was 14. Let's assume an infectious period which has mean duration 1, so maybe we measure time in terms of infectious periods, and the transmission probability P. Then the reproduction number is just simply this transmission rate times P. And that's the basic reproduction number. You can compute the final size numerically using this well-known function for the final size, and I call that the homogeneous model. Then we do the same thing in the way I just described, where we acknowledge the different age groups. I call that the A model, so A for age. But then I do another thing, or we do another thing. We forget about age, and we classify individuals into the low active and the high active individuals. So just two classes of individuals. I call that model the, oh, a lot of text here, the S model. So we have a group of 50% people with highest number of contacts is one group, and the 50% with the lowest number of contacts is the other group. And then we treat that as a multi-type epidemic. There's one problem though. We know in the high group, we know what is the average number of contacts, but we don't know who they have contact with. We don't know if they tend to have contact with other highly socially active people, or if they tend to have most of the contacts with the less socially active. So we consider three cases. I will only describe two here. The fully assortative model, where assortativity is with respect to social activity. That means that the highly socially active more or less only have contact with other socially active. That's called the assortative. And the low with low. The disassortative, you cannot do exactly the opposite, but more or less the opposite. So you mainly have contacts. If you're highly socially active, you have most of your contacts with a low social active. So this S model comes in two versions, the assortative model and the disassortative model. And we fit it to the data. We assume 50% of both times, still a mean infectious period. And for that model, we can compute what is R0 and how many will get infected. And the fourth model, we do both things. So we admit we have 7 age classes, but each age class we divide into the socially active and the socially less active. And we know the socially active in a given age class. We know which different age classes they have contact with, but we don't know if they tend to have with a socially active in each age class or not. So also that model comes in two different versions. So the AS model also comes in a assortative version and a disassortative version. There is an intermediate thing called the proportionate mixing, but I won't show slides for that here in this presentation. Okay, so for the same data set, we analyze it in 4 different ways. This is the old style, and this is what has been done for the last 15 years. And now we have added social activity, neglecting age, and having both age and social activity. Of course, we don't know what is a true model. Well, we know that neither of these models is a true model, but one would hope that this is probably the one that fits best to reality, since we include both type of heterogeneities, and this is probably the worst. So I guess maybe an interesting thing would, does it change much from going here to here? So is the A model quite close to the AS model? And then also, how about the thing where we neglect age? Is that one closer to here or closer to here? Maybe you can guess the result, since I'm standing up here talking. So wind up, yes. So let me just look. So here is the result, and the result is that the homogeneous model and the A model, admitting age differences, are very similar. The big difference here is when you admit social differences in social activity, and adding age doesn't add much that more. So the main conclusion is that the age do change a little bit. You see that you get a higher R0, as I said, if you add age. But the big difference is when you admit that there is social heterogeneity, whether you acknowledge the age groups or not. Here is for the final size, looking similar. So it's the A and the S model are, the homogeneous and the A model are similar, and the social activity group. This is an artifact of the fact that we only have 2 age groups. Let's see if I have some more. We did some other studies for some other social contact data, more or less the same. Then we searched in all this, and we found one data set where there was no such strong thing, and that was a Vietnamese study. And here you see the variation among contacts is much less. So then it doesn't really matter. So the conclusions that we have, seems to be valid for nearly all contact studies, except some extreme ones like this Vietnamese. That if you go from homogeneous model and acknowledging age, that does make a difference, but not such a big difference. But when you add social activity, you get a rather different picture. So two social activity classes actually gave a much more better fit, closer to reality, than having, say, 7 age classes. And also this assortativity or disassortativity also made quite a difference. Maybe I didn't highlight that, but that was also evident from the figures. What does this mean? It means that future social contact studies should try to get some information if assortativity with respect to social activity, if social activity tends to be assortative or disassortative. But also in future, people should also take social activity into consideration. One thing is the following that's worth mentioning. Even if all had the same mean, there would be some random fluctuations, and if we split it up into two halves, we would still see differences. So how to compensate for that? But in the data sets we saw, there were very, very big differences between different groups, and they were followed up, so there were people systematically having much higher contact numbers and others having much lower contact. Okay, thank you very much.
At the expense of your coffee, let's have a couple of questions. So, it's Hans and
Can
then...
you go back to the previous slide? So you say it's a big difference even if you have only 2 classes. Why is it not because you have only 2 classes?
No, we also tried splitting social activity up. Since there were 7 age classes, we also looked at splitting up social activity into 7 different levels of social activity, and then the differences became even bigger.
Yeah, but then you need to make more assumptions about who mixes with whom, right? Again,
Yes, and we looked at the 2 extremes.
Lorenzo.
But you're right, the more classes you have, since we don't have information, we have to make some assumptions. There is more information missing, that's correct.
Thank you, Tom. That was great. I wonder, when you compare models, it's always a bit difficult to decide what you keep fixed between models. So in this case, you kept fixed P, right?
Yes, so the plots were as a function of P. So, yeah, so we used the same data to estimate the contact matrices. And other than that, we had the same infectious period and the same P for the different models. Yeah.
Because another way to compare the models would be to kind of try to have some data about the, say, the early part of the outbreak, and then try to fit the different models to the same growth rate, which is a different approach. I was wondering, you might still see a difference. My guess is probably less extreme than you're seeing now. But I was wondering whether you would...
No, that's an interesting comment. So you could calibrate in a different way. Let's say that you observe this initial exponential growth rate, and then what would be your conclusion? Yeah, that's a different type of calibration that would be interesting to study. Yes.
I'm sorry, there are quite a few people still wanting to contribute. Just take Matt as the next one, and then we'll have to
ask a quick question. I mean, one of the issues with these contact surveys is that you have someone who says, you know, I've had 1,000 contacts. We know that those are going to be very, if they're real, we know they're going to be very, very short. And so the transmission probability across that contact is going to be a lot less. So it's something, I mean, we've been doing something actually very, very similar to this, so it'd be good to have a look at briefly. But have you actually thought about what to do with these extreme individuals? Because obviously they're not going to generate 1,000 cases. It's going to be much, much smaller. I'm just wondering if some of these things disappear if you take into account duration of contact or strength of contact.
Yeah, that's an interesting comment. We haven't done anything here with that, but 15 years ago I wrote a paper with a sociologist that was sexual contacts, and then his idea was that if you have one partner, you are more likely to transmit during a year than if you have 100 partners. You're less likely to transmit to a specific other individual because it might be a one-night stand. So And that applies probably to all other contexts as well. So here we have not taken this into consideration. But I guess it's not taken into consideration when you look at the mean matrices either.
Okay, I think I'm going to stop this now. There are lots more questions, but I think we'll have to take them over coffee. So thank you again.